You gonna stay there?
I can.
Okay. Don't move.
Do I have to?
Don't move. No.
You're allowed to take off your mask.
Yeah, actually, it's probably a lot nicer.
Yeah. Yes.
Saves a bit of, I guess there's enough space.
Yeah, we got the double filter.
Nice. I got my booster shot actually a couple days ago now, so extra protected.
I checked a couple weeks ago and I couldn't find any.
It was very difficult, but I think there was a spike in people trying to get their booster shot right after the news of Omicron. So it really was mostly, I think it's getting better again now. Can I not move too much? This is fine.
Try to move between there and the light screen there.
Okay,
Yeah.
Don't go out.
I'll know. I know my boundaries.
Yes. All right. So I think we should start. And today we welcome Lieke van Son for the last colloquium of the season. Lieke is a graduate student, and she's joint program between Harvard and the University of Amsterdam. She's an expert in gravitational wave progenitors, massive star evolution, and today she's going to talk about the redshift evolution of the binary black hole merger rate awaiting matter.
Thank you, Fabio. Thank you for the introduction, and thanks everyone for coming and giving me the opportunity to speak here today. Indeed, I'll be discussing the redshift evolution of the binary black hole merger rate and why that is a weighting matter. And that is at least for two reasons. First of all, I think we can learn a lot of the redshift evolution of the binary black hole merger rate, both about the formation of these black holes and about the high redshift universe from a completely new perspective. But I also think it's a weighty matter because I think the redshift evolution will be mass dependent. And I hope to convince you by the end of this talk that this is at least something we would expect from isolated binaries or stellar evolution. But before I dive into the high redshift universe, let's take a step back and start with today. As most of you will probably have seen, about a month ago, the third catalog, the Gravitational Wave Transient Catalog 3, was released by the LIGO-Virgo-CaGRA collaboration. And this allows for us to make these beautiful posters of all of the gravitational wave mergers that we've observed since 2015. So I always love to keep in mind how impressive it is that we've moved in 6 years from a couple of mergers detected to like 10 mergers detected to about 90 detections today. So we're already seeing some exponential growth in there. And this is only just the beginning. So the question that keeps me busy, I wouldn't say, well, sometimes up at night, but mostly up during the day, is how can we use this ever-increasing database of merging binary black holes to learn something about their formation, the formation channels, the physics that govern their progenitors, which are mostly massive stars, which I'm very interested in personally, but also cosmic star formation history from a completely new angle, namely from a gravitational wave perspective. So to focus on the start, if we want to understand or if we want to make some progress on understanding where these binary black hole merging binary black holes come from, we have to have some idea of how they form. So basically, all these formation channels have to answer the question, how do you get two black holes so close together that by purely gravitational wave radiation, they will merge within the age of the universe? Because gravitational wave radiation depends on the separation to the power of 4. So the in-spiral time depends on separation to the 4th power. And so you really need to place two 30 plus 30 black holes need to be at a couple solar radii within each other to be able to merge them. But their progenitors, namely massive stars, are a little bit like humans in the sense that when stars get older, they get a bit bigger and fluffy. And so if you would place two black holes very close together, and if you would put progenitor stars at the same radius, they would be completely overwhelming each other. It would just not fit. So you need to find ways to bring these black holes closer together in after the fact, kind of. Luckily, astronomers are very resourceful, and there have been many, many formation channels proposed to date. And this also leads to a very wide variation in the expected, the predictions, the predicted properties, predicted rates, mass distributions, etc. However, broadly, we can kind of subdivide all these formation channels into two big categories, namely channels that only need, we call evolutionary or isolated binary channels that only need an isolated binary that evolves further and dies as an isolated binary black hole, or dynamical formation channels where external forces are come in play and they help to bring the black holes closer together. So again, with this isolated binary evolution, I mean, we start with an isolated binary somewhere in the galactic field. It evolves, and through multiple phases of mass transfer and binary interactions, we manage to shrink the orbits of the cores, and we can end up with a binary black hole that is close enough together to merge within the edge of the universe. While for dynamical evolution, you can have binary stars, but also single stars live their life in their own. And if you have a dense environment, you can have dynamical encounters where usually this leads to an exchange of partners, which tends to harden the binary, giving you, again, a merging binary black hole. So to make progress, of course, we want to observe, or we want to compare all the predictions that come from these different channels to the observed source properties. And we're at a very unique and exciting time, where the first time we have enough data to make some meaningful comparisons between the different properties of the black holes that merge and the predictions that we get from our theoretical models. So mainly, we're starting to see a lot of structure in the black hole mass distribution. We're starting to constrain some parts of the black hole spins, and also there are binary properties that we can observe, so like the mass ratios, the eccentricities, and the tilt of the spins, so the precession, sorry. So let's start and try and compare these to those broad formation channels. First of all, dynamical formation channels, this is a really funny video from Carl Rodriguez that just shows how such a dynamical encounter would work. And if you pay attention, it ends up exchanging, and in the end, you end up with a closer orbit. To have these kind of interactions happen, of course, you need a very dense environment. Dense environments are generally more rare than the field. But this also So that constrains the rates that you can get with this formation channel. But also such a very chaotic interaction causes you to predict or expect that the incoming spins of black holes are isotropically distributed, because basically you just throw a bunch of black holes at each other and they all have, they do not per se have to have their spins aligned with the orbits. Now, if we look at the effective spin distribution, which is some form of a mass-weighted spin for the binary, we see that an isotropic spin distribution is not exactly what we're measuring. The LIGO Virgo black holes seem to have some preference for aligned spins and mostly low spinning. So this does match more to isolated binaries, where we expect that the mass transfer phases tend to align the spin of the black holes with the orbit of the binary. So let's, yes.
This is now observational evidence, right?
Exactly.
And you're saying that it's tilted a little bit away towards positive spin.
Yes.
But how should I interpret it? Because to me, it looks like the shift is less than 1/6.
Yeah.
Is it significant or?
It's a good question.
Yeah.
I think, okay, I didn't want to dig into this too much, but I think there's a lot of prior domination going on still with this, the shape of this distribution. And honestly, I think if they would have chosen different priors, this negative spin part could go away completely. And so we're not at a certain moment that we can say, yes, we know this is the spins and this is all there is. But I think there is more evidence pointing towards things have low or positive spinning than there is towards anything having a negative spin. And another way to say this is all of the systems individually have posteriors that are consistent with 0 or positive spin. And there's only a couple that are also consistent, that have posteriors that are also consistent with maybe having some possible negative spin. I hope that answered my question. Yeah.
And of course, to be in a system, you have to be in a similar environment. And is it likely that the environment is transferring negative momentum to everything in it in a way that systematically favors the same spin?
So for the dynamical channel, I don't think there is any, the spin comes in from the alignment basically, or the orientation that the black hole had when it came in and met the other one. And that is expected to be isotropically distributed. And so that should give you a random orientation.
So in no sense, like a medium or environment that they're both in, because they would spread out so far away that it's really just not any effect on the spins of both of them.
No, not for the dynamical. It really is, it comes down to what is the spin of the thing relative to the orbit, and then you can really have, it should be. I hope I understood your question.
I was just wondering if there's like.
No, for binaries, yes, because then they will get aligned more because of the mass transfer. Yeah. Okay. So let's move back to isolated binaries then, where I've drawn this simple schematic of what the life of binaries could look like before they end up dying as two black holes. But unfortunately, also among isolated binary evolution or binary evolution, there is many unknowns left. There's lots of uncertainties. However, there's one prediction that comes from stars that is relatively robust, and that is that we don't expect stars to make, or single stars at least, to make black holes with masses in between 45 and about 140 solar masses. And that is due to something called pair instability supernova, which means that if you have a core of a star that is big enough to form a black hole of about 45 to 140 solar masses, this core becomes hot and dense enough that it allows for spontaneous pair production. Now, if you're starting to use photons to make electrons and positrons inside a core that was really using those photons to prevent itself from collapsing, then you will start a sudden collapse, which will ignite oxygen in these cores, and it will give you an explosion that is basically premature and will throw off a lot of mass in some cases, or it could completely disrupt the star and leave no remnant whatsoever. And that is what this plot shows as well. Here, if you have an 80 solar mass star at start, even though the core becomes bigger than a 70 solar mass star's core, it will start to lose a lot of mass due to pulsations up until at some point there's no remnant left. So this red curve is basically the black hole mass that you can get. And this shows here that the maximum black hole mass that we expect is around 45 solar masses. But looking back at this distribution, we don't really stop at 45 solar masses. There have been definite detections of systems with 80 solar mass black holes in them. So basically, this brings us in an overview saying that probably we need multiple channels to explain the full distribution. But it's difficult, right? Because a lot of these channels have overlapping predictions, and we want to make progress. We want to exclude things. Luckily, as I said before, we are really only just at the beginning because this growth is going to continue. This is an expectation of the size of the catalog that we will have as a function of time. And we're here at the end of the third observing run. And indeed, we've seen about 100 black hole mergers, binary black hole mergers, a little less. And we've seen on the order of a couple of binary neutron star and neutron star, 2 neutron star black hole mergers. But this is what the coming decades are holding or promising. So even at the sign sensitivity will go up almost an order of magnitude. But in about 10, 15 years from now, we'll have around the order of 1 million binary black hole mergers. So we really want to understand and we want to prepare the theory to be able to harvest all this data. And there is another important point that so far I've been really focusing on distributions that we observe at low redshifts, but also for the first time, LIGO and Virgo have been able to confirm that there is evolution in the rates with redshift, and they have some constraint of what the evolution of the binary black hole merger rate with redshift will be. Even though it's still very broad, I think it's incredible that we're already having some constraint even up to redshift 1. But again, this is just going to get so much better, because this plot shows the horizon redshift for a certain source frame mass. So this means for higher mass black holes are louder, and so you can see them further away. And this blue curve shows that LIGO indeed will see up to somewhere a little bit beyond redshift 1. But these third generation detectors are going to see the whole universe, basically. So even beyond the first star formation history, if there are any black holes, they should be observable. So that would be a great thing for primordial black holes if they are there. And specifically for the range of stellar mass black holes that I'm very interested in, we are seeing out to these extreme redshifts. So that brings us back to these questions. How can we use this database to learn something about these things? And now I also want to focus on this last point a little bit about cosmic star formation, because really if we understand how the rate evolves with redshift out to these extremely high redshifts, that can of course tell us something about how many stars have formed at these very high redshifts. But to make some sense of this high redshift or this redshift evolution, we have to understand that merger redshift is not formation redshift. So made another nice little cartoon to show what kind of timescales are involved in a binary black hole merger. If you start over there on the left with a Big Bang, and at some point in the galaxy far, far away, you form a massive binary star. Massive binaries only live for a couple million years before they die. Maybe, and luckily, you can form a binary black hole. But then between the formation of a binary black hole and the merger as a binary black hole merger that we observe today, there can be anything between a couple million years or many, many giga years. And this in-spiral time can vary broadly based on the properties of this binary black hole, namely the eccentricity, the mass, and the separation, where the separation comes in most. So we call this time between the formation and the merger the delay time. And we will be observing this merger rate from the right side, but we want to know something about their origin. So we would like to understand the distribution of delay times. Unfortunately, delay times are not an observable. We observe masses, we observe spins, mass ratios. So in order to make progress here, we would really like to link delay times to observable properties. And that's exactly what I set out to do in other work for specifically isolated binaries. We were asking ourselves, do we expect any correlation between between black hole mass and the delay time? And if so, how would we observe such a correlation between delay time and black hole mass in the rate redshift evolution? So I'm going to spoil and immediately give you the answer before I explain why. Yes, we do expect to find a correlation. And this leads to 2 points. We find that we expect a distinct redshift evolution for low mass black holes versus high mass black holes. And we also expect to find fewer massive black holes at high redshift, which is something that surprised me at first because of a Metzelisty argument that I will get into a little bit later. But first, do we expect any correlation between black hole mass and delay time? Well, to answer this, first want to explain that even within the isolated binary channel, there are, of course, many subchannels that leads to binary black holes. But also within the isolated binary channel, you can probably make a divide between 2 things. The first thing is, has this binary experienced unstable mass transfer or a common envelope? So in other words, a common envelope. Or has this binary never experienced a common envelope and only experienced stable Virchow overflow, so stable mass transfer? And that matters a lot because the separations that you get from these different channels, the final separations that we expect from a common envelope are much smaller than the final separations that we expect from stable Virchow overflow. This difference has been exploited before by other people. So Simone Bavera has looked at the effects that these 2 channels have on the spin distribution of black holes, where these are models that show the mass and spin for the stable Virchow overflow channel and the common envelope channel. And as you can see, for the stable channel, everything is basically 0, while for the common envelope channel, they form spinning black holes. This is because these separations cause the stable Virchow overflow channel cause these stars to be wider. So you end up with a helium core and a black hole that are too wide to allow for tides to spin up the core, whereas for common envelope channel, you have a very tight orbit, black holes plus core, and so this allows for tidal spin up, giving you at least one spinning black hole. So this is about spin, but what do these channels predict for the black hole mass and the delay time? In order to answer this question, I used a population synthesis code called COMPASS to basically translate a lot of assumptions about initial conditions, about binary separations, initial mass function, etc., into a final distribution of delay times and black hole masses. And we translate, what I show here is basically the distribution of primary black hole masses, so the more massive black hole, and delay times for black holes coming from, emerging black holes coming from isolated binaries. And as you can see, there seems to be a dearth of black holes in the upper left corner. So that means that we don't seem to form massive black holes with more than 30 solar masses and short delay times, less than a gigayear. And if we split this diagram up between things coming from the envelope channel and things coming from the stable Redshift overflow channel, we see where this difference seems to come from. Specifically,
So are these models or is this the data?
this is models. This is, yes, sorry, this is a theory only from an isolated party. So we see two very specific things in this data, in the models.
These are just Monte Carlo models where you randomly pair and see.
Yeah, well, it's actually adaptive inverted sampling, so we do a little more than to really try to get as many emerging black holes as possible, and we try to mimic initial distributions that are thought by observation. So we have similar initial mass functions, period distributions, etc.
And you don't find a dramatic difference depending on the IMF that you choose, or is there?
So there is this paper from Belczynski and Selma a couple years ago where they tested for all these things, and the rates for IMF and period distributions, etc., they don't change too much. The IMF can have a difference, but I think the bigger difference will be in the different cosmic star formation history. But because what I'm showing here is really just the data, not weighted by the metallicity specific star formation rate just yet. This is just what rolls out of our data, basically. I think because this is really empty, it's quite robust. Like even if you reweight this in very different ways, you will still not have many high mass black holes on this side, and the same on this side. Specifically because we understand why we don't form high mass systems here and why we don't form short period systems here. And I think given the uncertainties that we have in the modeling, this effect will only become stronger if we take into account this. So I'll discuss this in a little bit more. And we just first, emphasize, so the common envelope systems don't seem to form anything with more than about 30 solar masses. And the stable Redshift overflow channel doesn't seem to form any short delay times. Just summarizing that again here. So let's dig into this a little bit. And this is a bit technical, but so why do common envelope systems not like to form high mass systems? Well, it all comes down mostly to, if you want to form a high mass black hole, you need a high mass star. Very massive stars appear to be, or we find them to be, very reluctant in both engaging in a common envelope and surviving a common envelope. This is the case because very massive stars have very high winds, so they have very little envelope left to go into a common envelope. But moreover, these massive stars are so hot that they typically have a radiative envelope, not a convective envelope. And convective envelopes are what give you, what lead to unstable mass transfer typically, because if you take mass from a convective envelope, the response of the envelope will be to expand. Whereas if you take mass from a radiative envelope, the response will be to shrink. And so you don't get this runaway common envelope effect for these hot, massive stars. And there's actually a lot of work, there's a lot of literature right now that are arguing more in favor of this. In specific, Monica Gallegos Garcia and Pablo Marchand and Jakob Klenke, they are all running detailed evolutionary codes, and they're saying these massive stars all shouldn't really go common envelope. It really, stable Rorschach overflow should be more dominant for these more massive stars.
So this clearly cannot be interpreted as an IMF issue. It was just making
Exactly. Yes. So that's what I'm saying. So the rates will change, but because we know where this comes from, it is not an IMF thing. If you just form more massive stars, they would still not go. Initial mass function. I'm sorry. Yes.
Oh, sorry.
Yeah. Yeah. So that's just basically how many massive stars do we start off with. So yeah, you can be weighed up and it doesn't change. Now,
The convective versus radiative is which is the dominant method?
yeah, so typically people assume that a convective envelope will lead to, if it starts transferring mass while it has a convective envelope, this can lead to unstable mass transfer more easily. It is not one-on-one. There's a lot of details in mass transfer stability and the way that these envelopes work, but especially because what I was saying, these convective envelopes will respond in a different way to mass being taken off. And they're also, the density profile of such convective envelopes is a lot more flat, which means that there's a lot more mass towards the outer side of the envelope, which makes it easier to take off as well. Whereas if you have a radiative envelope, the profile is more steep, the density profile, and so it's harder to actually take it off of the star. And so, yeah, hotter stars are more have more radiative envelopes, and more high mass stars have are hotter. So the other channel, why doesn't the stable Rorschach overflow channel lead to these very short delay times? Well, I already alluded a little bit to this. That really comes down to the in-spiral time, depending on the separation to the power 4. And common envelopes are really, they're basically brought into life because we wanted to get things on very short orbits. So they're really efficient at shrinking the orbits to very small distances. Whereas the stable Rorschach overflow, the mass transfer can shrink, but also widen the orbit during the mass transfer. And the final separations that you end up with are typically a lot wider. This was known already before, but we hadn't really realized what the effect would be on the distributions. So if we look at what a modeled distribution of the mass distribution would look like, given Einstein binaries, we see also that there's a very interesting subdivide between these two channels and what parts of the mass distribution they cause, where the common envelope channel is the one that is responsible for all these lower mass systems, dominates the low mass end of this mass spectrum, but the stable Rorschach overflow channel takes over on the high mass end just because the common envelope becomes very inefficient at producing black holes there. So all of this was still just talking about the effects, the pure binary effects, but how will we measure this correlation between black hole mass and delay time in a redshift evolution of the merger rates? Now to do this, we've taken a star formation rate density, namely we've used the Metalisty dependent star formation rate density from the TNG 100 box to place our binaries in a cosmological context, basically. And what I'm showing here is the rates of the binary black hole, the binary black hole merger rate over the rate at redshift 0 as a function of redshift. And I use this so we can focus on the slope of these merger rates. So let's see what happens if we add on the low mass black holes. So basically the black holes below 10 solar mass, between 10 and 20 solar masses. These are the black holes, if you remember, they come mostly from the common envelope channel. And so they have typically shorter delay times, which shows in the fact that they are very much following the star formation rate density, because they're formed and very quickly after they merge. If we go to higher mass black holes, which I've just shown are mostly dominated by the stable version of overflow channel, the distributions are much flatter and the slopes are lower. And the peak of the black hole merger rate happens at progressively earlier redshifts. And this is also due to this black hole mass delay time effect, because due to these long delay times, basically some of these black holes haven't had time to merge yet. So even if you form out here at the peak of the star formation rate, you still need many giga-years to merge, bringing a lot of the stable version of overflow distribution, pushing it to lower and lower redshifts where they would like to merge. And so this is why the low mass black holes follow the star formation rate density. The high mass black holes have flatter curves and peak at earlier redshifts. And so we have looked for evidence of this in the current gravitational wave transient catalog, but it's still very hard to see any redshift evolution in the binary black hole merger rate because we don't have that many detections yet.
So very quickly, Lieke,
yes.
I wanted to now look at neutron star binaries, double neutron star or black hole neutron star.
Yeah.
Is it just going to follow the low mass black hole curve?
Not exactly, but more, because there's two things that come into place. First of all, the formation channels for black hole neutron stars and neutron stars are mostly dominated by the common envelope channel, much more than for the binary black holes. So indeed, they would be following more the short delay time and star formation rate density, but there's a second effect, and it's the metallicity dependence. And so black hole formation rates are very metallicity dependent and not so much physics variation dependent. On the other hand, the neutron star mergers and black hole neutron star mergers are more dependent on the assumptions that you make in the binary physics there. And so those could change what the shape of the redshift evolution looks like. Though a fiducial model, I would expect indeed would follow the star formation rate density like these. I just wanted to emphasize quickly that maybe today we can't see this yet, but what I'm showing here on the right axis is the percentage of the population that will be detected with Cosmic Explorer for different source masses. So this is for this is basically the lower edge of the black hole distribution, 2 times 2.5 solar mass, up to 25, 2 times 25 solar mass, which is not the top, but it's starting to get very crowded up here. And you can see that this region of interest where we predict these different slopes, basically all of the stellar mass black holes should be detected. We have like more than 80% of all of these stellar mass black holes in the near future. So it's not just a prediction, it's a testable prediction. We will be able to rule out if this doesn't happen. So just summarizing again, we expect low mass black holes to follow star formation density, and we expect the high mass black holes to follow a different evolution. But so how would this look like if we look at the evolution of the mass distribution itself? Because again, these are these two components that evolve differently with redshift. To show this, to emphasize this, what we did was just basically show the same plot. We showed the same plot, but then normalized by the peak rates in the distribution. And I'm plotting it for the different redshift spins between redshift 0 and redshift 2, where the dark blue is low redshift and the light blue is higher redshift. And as you can see, the right-hand side of this mass distribution is falling off quicker than the left-hand side, which means that we're expecting to see relatively fewer high mass black holes if we go to higher redshifts in the mass distribution. Now, I mentioned a little bit earlier that this is a surprise, especially for stellar people. We think a lot about winds.
Pardon me, I don't think I followed that claim.
Sorry,
It
yes.
says the right-hand side is falling off quicker than the left-hand side, but the left-hand side slopes are manifestly like almost horizontal, and the right-hand sides are pentagonal. So what do you mean when you say the one is falling off faster than the other?
I mean more that the ratio between high mass black holes and low mass black holes at the moment is different than the ratio between the high mass black holes and low mass. So if you would basically bin this in two bins, high mass somewhere at 25 and say high mass and low mass, then we have a higher ratio of high mass to low mass black holes today than we expect to see at higher redshifts. Sorry for miswording a little bit there. Understand the confusion. This is surprising because it's very unique, kind of. Most people who think about formation channels would tell you if you go to high redshifts, you will have lower metallicity. The universe had less star formation happen, so it's lower metallicities. Lower metallicities will lead to weaker stellar winds. And if you have less winds, so weaker winds, will lead to higher mass black holes. So naively, you would expect to find more high mass black holes at high redshifts. However, the results that we're presenting today show that this is not necessarily true. You really have to think about the delay time distribution before you can make such claims. Because if the high mass black holes are biased towards having longer delay times, which we find they are, you expect them to see them merge today rather than at high redshifts. And again, so this might be a distinguishing feature for isolated binary evolution, because dynamical channels typically tell you that higher mass systems have shorter delay times because their high mass also comes into play with the in-spiral time, and they have much higher masses there.
So low metallicity is necessary, but it's not sufficient to make a lot of high mass black holes.
Yeah, exactly. So this is still true. So I do expect high mass black holes to be formed at high redshifts and with low metallicity. So you do indeed need low metallicity to form a black hole, high mass black hole. But to see it merge, you need to know how long it takes to merge. So you need to understand the delay time. And that is a key aspect that we should take into account. When normally people would think, oh, low mass black holes and high mass black holes have the same delay time distributions. So you form more high mass black holes at high redshift, you probably see more high mass black holes at high redshift. But I don't think that is true.
So, a lot of the argument that you're basing this on is on the globally average star formation rate. What you are really measuring with LBK are sort of really local, very local to our galaxy, right? So it's a bit of a leap in terms of statistically how representative.
That's a very good point. And I do 100% agree that the star formation rate density is going to be one of the things that will change these results a lot. I have tested this for multiple star formation densities, and the fact that you get different, like stable reversible overflow from high mass, common envelope for low mass, that's not affected. And then when you form them depends on the star formation rate density. But I found for these different star formation rate densities that you still get a different slope for high mass and low mass black holes. However, you can also turn this around, and that's what I'm hoping to do, and say like, if we don't observe this, or we are going to see to higher and higher redshifts. We can basically falsify a lot of these channels. If we don't see any evolution like this, then either there's something completely different with the star formation rate density, or there's something completely different in the things that I've been just discussing. But I think most of the things are very broad in models. That actually brings me to my next slide as well. Because indeed, it's great, it's good. Everyone should be asking, how robust is this really? Is this just one model that predicts this? But I want to argue that this is a surprisingly robust result, because as long as isolated binaries are in some way dominant to the rate that we observe, and both the stable Rorschach overflow and the common envelope channel contribute to the black hole merger rates, we expect them to give a distinct evolution, namely, and there's point 3 and 4, if they still both lead to different final separations, and so different delay time distributions, and these distributions are observationally distinguishable, we expect to see a different evolution in with the rates with Redshift for stable and for common envelope channels. And I'm specifically saying observationally distinguishable because I want to take this more broad. I've been really focusing on the black hole mass because that's the prediction that we found that's different between stable and the common envelope channel. But as I showed somewhat earlier, there's more observational characteristics like the spin that could also be different between these channels. And that could also be a marker to help us figure out which black holes come from where.
Is there anything that's an intermediary between Rochelle, which is basically one of the binary members versus the common envelope? Is there maybe a very small envelope around one and much larger one around the other, or is this like very distinct observationally clear cut different?
So they're unfortunately not completely clear cuts, but they do give quite separate distributions, which is why I'm so happy with it. But it's definitely not all completely separate, because even though on average one gives short separations and the other gives wide separations, there's also things like natal kicks that you have to take into account. If you get a lucky kick, you can always get to a smaller orbit, or you can get a quick merger. Of course, there's also somewhat outliers towards, it's very difficult, but if you, there are some specific channels through which you can still form a higher mass black hole that has still experienced a common envelope, but it's just a lot more rare. So it's not, unfortunately, completely separate, but there is a distinct distinction to be made. So these are 4 points, and these 4 points are relatively broad. And I hope that we can, if we continue to not observe any redshift evolution, we are going to have to reconsider some of these. Maybe this stable Rorschach overflow and common envelope channel are not both contributing. Maybe one or the other is just not a thing at all. Maybe we completely misunderstood how angular momentum transfer works in these stars, and the separations will not be very different. I think in general, there's always a way out, obviously. But I'm just happy with the surprising robustness of this result and kind of broadly, you can find it broadly in different models. So yeah, the summary of the expectations that come out of this work are basically we expect the common envelope channel to lead to low masses with short delay times, the stable version of the flow to lead to high masses with longer delay times, and the black hole merger rate should be different for different masses. And this will be observable. So we can throw this out the window if we will never find it. So I just want to end with a kind of a broader picture and zooming out again before I take questions. Typically, I think I want to say we should no longer ignore redshift illusion and redshift evolution. And with me, I mean the formation channel theorists among us that are mostly trying to fit the low redshift distributions right now. And we are living in a really exciting tipping point in the amount of data that we have, that we are starting to be able to make cuts in these all these formation channels. And we need more and more predictions from each of these channels to say, okay, this is really a unique characteristic that helps us exclude and make progress in finding out where all these beautiful black holes are coming from. So yeah, I think that brings me to the end. Thank you all very much.
Thank you, Lieke. Questions? Angelo.
So we've talked already about assumptions about the distribution of black hole masses.
Mhm.
One thing I want to know more about is what is known or assumed about the initial separation distribution?
Yeah, so what I've used in this work is just a flat and log distribution, but you can also use different like SANA 2012 distributions that are slightly more updated. So as I mentioned a little bit before, this seems to not have a huge effect on the rates predictions that we get. And with huge, I mean within a couple of factors, factors of a few.
And so flat and log space, is that just a pure assumption, or is that constrained?
That is somewhat observationally motivated, but
Okay.
You can make more elegant models that have more parallels, basically. Yes.
Mostly you talked about mass.
Uh-huh.
But in one of the slides, you showed some predictions for spin,
Yes, exactly.
and I presume those predictions come from some calculations based on tidal interactions
Yes.
during the various phases. I was just wondering, since these are very short-lived systems, do we understand tidal interaction physics well enough to really make, this is the slide, to make these predictions?
Okay, so I personally leave out tidal interactions and spin distributions exactly for this reason. So this usually what people do is we do this post-processing. So basically they just say we evolve things specifically for this system, for this work. What they did is they took Mesa evolutions and then they took the final separations of black holes and helium stars. And then they said, okay, what would the tidal interaction be? And they made some fit to that to get some sort of a analytical prescription for the spin distribution. I'm not 100% sure that this is at a level that we can use it to compare directly to the data, but then on the other hand, the data, the spin is also very hard to measure in the data, so you have a lot of fudge room there. What I do think is very interesting as just a takeaway here is that if you just are too wide to have any tidal interactions be of importance versus if you are at short orbits and tidal interactions could be a thing, that distinguish that that could already give you a distinguisher between these two things.
Except that, the common envelope is such a short-lived phase.
Yeah. No, but it's post common envelope that is the point, right? Because then you have common envelope is just how to get them close together.
Oh, so you're saying the spin-off happens after that?
Yes.
Oh, okay.
Sorry for
that
not
was a
being
little
clear.
bit. Okay.
Yeah.
more questions. Yes, Sanjay.
On your plots where you have rates as a function of redshift for different masses,
Yes.
I'm wondering if what is the state of the dynamical or other models in producing a plot like this? And is there, for example, a redshift or mass where you think this other channel is going to dominate now and we shouldn't?
There is definitely thought. I'm sad that I didn't add some, but Nicola Matelli has done some work on this and their Redshift evolution. And basically they show evolution as well. But what they are saying is more that there's stronger evolution in the dynamical channel because all the way the other way around, these more massive things. I hope I'm saying it the right way around. These more massive things interact earlier dynamically. They're more likely to interact. They're heavier to interact, and then they basically get kicked out after they merge. So they only occur at the higher redshift. But it's good to keep in mind that the range of masses that these different papers, different people are looking at differ slightly, because I focused on everything below the parent stability mass gap because that's where isolated binaries are going to produce by far the most systems. But these dynamical channels often try to get more massive systems as well. So they focus more on black holes that have 60 or 70 solar masses due to having already experienced a merger. And so that also comes into play with why this redshift evolution is different, or they make different expectations, because for us, the ranges of masses that we're interested in are not super large. It's between 10 and 45, like 2.5 and 45 ish, whereas they go up to more than 100. So that m to the power 3 that comes into the in-spiral time becomes more dominant as well if you have these dynamically formed systems.
So this is, I think, a very naive follow-up to Ramesh's question. If the common envelope mechanism is there to get them close together, but whatever process it is that aligns their spins happens after the common envelope phase, why don't we see the same effect with the Roche slope overflow? Because the Roche slope overflow, they start far apart, but eventually they get close together. So what's the difference?
So there's a difference in aligning the spin and spinning up. So aligning the spin is have the black holes spinning with the same orientation with the orbits, aligned with the orbits, and that happens during the mass transfer. So for both stable and probably during common envelope, definitely during common envelope, we expect the cores or black holes spin to be aligned with the orbits. But then there is how much they are spinning. And there's this paper by Fuller that basically says that black holes are born basically non-spinning from stars. And that has to do with the angular momentum transport in the star. But the argument is approximately this: if you have a core that is spinning inside a star and the envelope gets very big, if there's enough angular momentum transport between the core and the envelope, then the envelope becoming big basically spins down the core. And if then that core collapses to a black hole, it's a lowly spinning or non-spinning black hole. That's the argument from Fuller 20, I forgot the year now, but 2019, I think. So basically this says all black holes are always for low spinning. But then there are models to do this, but it really depends on how efficient your angular momentum transport is here between the core of the star and the envelope. But so something you could do is you can spin up the core after it has lost its envelope. And that is exactly what's happening with this tidal interactions, where you have the common envelope and you lose the envelope and you bring the black hole and the core very close together, but you can still spin up this core before it collapses to form a black hole to get a spinning black hole. Whereas for the stable version of overflow, you have a black hole and a core that are both non-spinning and too far apart to have tidal interactions spin it up. Does that make sense?
Yes, thank you.
One more question.
Yes, go ahead.
Triggered by what I
Yeah.
asked. So yeah, so early on you talked about these two channels, right?
Mhm.
There is the dynamical channel,
Yeah.
this isolated channel.
Mhm.
And then you told us that the isolated guys, they won't make black holes more than 40 or 45 solar masses.
Yes, yes.
And I think you also showed a plot based on LIGO catalog 3,
Mhm.
that there is really no feature in the mass distribution in 45,
Yes, yes.
right? It looks like it's a continuous thing. Doesn't
Yes.
that prove that dynamical is the whole story?
Oh, that's a great question, but no.
Okay, tell me
I think
why.
I can tell you multiple reasons why. Okay, let me start. First of all, I was trying to be convincing and I said it's at 45, but obviously there's still a little bit of fudge factor and you can move it up and down a little bit. But there seems to be a problem in a mass distribution, which is very fun, and I could get a whole new talk about this. But there's bumps, there's features in a mass distribution, and those features are not at 45, indeed, very well observed. They're at 30-ish and at 9-ish. And now we don't know why there is a feature at 35 or at 30-ish, because mostly for the past 3 years, people have been focused on trying to explain why we see any black holes over here at all. And you can explain that with the dynamical channel. But no one has focused, because we didn't know yet, why should there be a feature at 30? Because when the first two catalogs came out, this feature was fudgy and it could be at 45, could be at 30. So people kind of grasped on and they said, yes, there's a feature at about 45, must be parent stability supernova. And now it moved to such low masses that maybe it's not parent stability supernova. Maybe this feature just comes from something completely different and we haven't seen the parent stability supernova cutoff at all. Now then your question is, why isn't this just all dynamical? Well, my main argument is not at this point for that, but at this point, because you cannot just explain only this part, you also have to explain this lower mass part, and dynamical channels don't really prefer to form lower mass black holes, because the higher mass black holes are the ones that sink to the center and that merge.
What's the detection cutoff on the low end?
The detection,
Yeah, how small can they get? Still be detected?
we can detect them way slow. We can detect neutron stars, so we can detect them down to a solar mass or lower. But the issue here will be the redshift. We won't detect them out to very high redshifts, but we have systems. We have enough right now to start to see that there's a feature that peaks at 9, and not at it. It could have peaked at 3 or 4. And then we would have seen that, but it seems to prefer more 9. And so not only is there a peak at 9, it is the highest peak at 9. So it's not just that there is some stuff happening there, but most of the stuff is happening there. And with isolated binaries, you can kind of explain that more naturally, because isolated binaries would like to form more low mass black holes. I think, but this is my current personal guess, which might not say much, but I think we might not have seen the parent stability at all. And these two bumps are just different bumps that come from the mass transfer stability in isolated binaries. And that's something I'm trying to look into and hopefully get some interesting answers for. But I expect you to see a lot of papers appearing in
the IMF. It could be.
It could not be completely IMF. I mean, I think.
The 9, for example. Could be.
Yes,
Not
but
the
then
10.
why is it not at 6? Because if it's purely IMF, then I would expect this to just continue up. But exactly the point that it's not just going up to lower masses, but it turns over. It seems like there's a feature. That's interesting. Why is it at 9? I didn't expect it to be at 9.
What I'm saying is one can reverse engineer and say, given that it's at 9, it might have an implication for a feature in the IMF itself. for instance,
Yeah,
right?
that could be. Yeah, that's true. Yeah, yeah. But there is also uncertainties in the, so my first guess would be uncertainties in the mass transfer, but also the mapping between final mass and core mass.
Core mass.
Like, yeah, because that is uncertain, and that is something that also this might hold valuable information about, that we can use this to constrain its mass.
All right, any more questions? So if not, let's thank our speaker again. Happy holidays.
Yeah.
Coming back in the third week of January. Happy holidays, everyone.
Great.
Merry
Good
Christmas.
talk,
Thanks,
Lieke.
Sonia.
Thank
talk.
you.
Oh, people are following your talk. They are
Oh, yeah.
Yes, I was surprised.
Very nice.
Very